Thank you very much, Rick, for the kind introduction. And okay, there are the slides. So unfortunately, Wei Huang, the first author of this work, couldn't make it here today, but I'm very happy to be able to present to you all on his behalf. And here's our disclosures. All the authors are employees of Topcon. So OCT has been used clinically in ophthalmology for about 20 years now. It started off with time domain OCT, running at about 400 hertz A-line rate. And by 2006, spectral domain OCT was commercialized, and line rates now are up on the order of 50 kilohertz, perhaps more. And then over the last several years, 1 micron swept source has entered the scene. And there the line rates can be 100 kilohertz or higher in research systems. There are a number of advantages of swept source over spectral domain, including greater penetration depth, improved signal roll-off characteristics that Rick showed earlier in his presentation. And that enables deeper choroid imaging, and that's facilitated also by a 1 micron light source that penetrates through the RPE more than the 800 nanometer wavelength light sources that are common with spectral domain OCT. And all this enables simultaneous capture of vitreous and choroid. On the lower left here, we see some images comparing SDOCT and SSOCT and their depth characteristics. For SDOCT, we can see the retina here very nicely when the image is positioned at the top of the display, but when it's positioned towards the bottom, there's a very high sensitivity loss, which translates to an inability to see the details in the image. With SSOCT, we see similar characteristics in the image, whether the retina is positioned towards the top or the bottom of the display. And also we note here that the display is even larger than it was in the SDOCT case. On the right, we see a pathological myopia case where with spectral domain OCT, even though the image is well within the display, we actually don't see the retinal details towards the top, towards the zero delay line. Presumably, the focus in the image is towards the bottom of the display. On the other hand, with swept source OCT, we see details throughout the entire image display. And this is a big part of why we named our swept source systems DRI, or deep range imaging. That not only are we able to penetrate through the retina and get a good view of the choroid, but at the same time we're able to see information in the upper part of the image and lower part of the image space. So we wanted to objectively quantify the effect of SNR differences between spectral domain and swept source. As I showed in the previous slide, there were qualitative images. We've seen many qualitative comparisons over time, but we think this is the first, or one of the first, objective comparisons between the two image data. So we went about collecting data on using the Maestro system as well as a Triton system. So Maestro's spectral domain, Triton is swept source. We collected 60 eyes from 30 healthy volunteers without media opacities. And the ages range from 23 to 67. We see the profile here. We collected image data for all of our standard imaging fixations, macula, disc, wide, and we made sure at least one acceptable scan for each of these modes was collected, and then we chose the first acceptable scan to utilize as part of our comparison. Now, we used SNR-based image quality indices that measure the the degree of signal distribution similarity between the foreground signal and the background signal, and I'll discuss those in the next slide. And we have two different measurement indicators. One is the Topcon image quality indicator that's built into the OCT systems, and that exists in both the Maestro and in the swept source, Triton. That's a little bit subjective because the definition is customized a little bit from machine to machine. So in addition to that, we also created more objective signal-to-noise ratio of specific parts of the retina, and I'll discuss that going forward. So how do we go about calculating or estimating the SNR? So first we segment the retinal image and come up with a background region shown here in red. Then the retina itself is identified and that signal is used as foreground. And the two are put together, overlaid, and the shape of the overlap is then quantified using a proprietary calculation. Now, one thing to note here is here we're actually calculating the extent of the similarity and overlap, not simply looking at the degree of overlap on the x-axis. So these calculations have a very high repeatability or a very low coefficient of variation associated with them. So first I'll show you top Q score comparisons. Here, the red are the spectral domain machine, and the blue is the Triton swept source machine. And we can see instantly on all three types of scans that the swept source uniformly has a much higher range of image quality scores. And we see that also statistically here in the table. And the mean differences between the spectral domain and swept source systems are all highly statistically significant as shown here. And one other thing that I'd like to draw your attention to, and we'll see this in all the results that I'm presenting, is specifically for the wide scan mode, which is 12 millimeters in length. On the spectral domain system, we see quite a significant drop-off in the image quality score, whereas in swept source, the drop-off is much smaller. So branching off from the top Q scores, we wanted to look more carefully using the more objective signal-to-noise ratio computations. And we created two separate calculations here, one for the SNR of the retina and another for an SNR of the estimated choroid. And once again, we see very similar sorts of results to what I showed in the previous slide. Again, swept source is uniformly significantly higher than the spectral domain, and the drop-off from the 6x6 modes to the 12 millimeter wide mode is much smaller in the swept source system than it was in a spectral domain. And we did the same for the optic disc and see pretty much the same trends. So we wanted to take this even further and look at specific characteristics of retinal layers and retinal regions. So we segmented the full 3D volumes into 9 layers using Topcon advanced boundary segmentation, what we call tabs. And the foregrounds then, rather than being the full retinal region, were limited to the specific retinal regions being examined. And I'll note here that the CC or choriocapillaris we defined as being about 10 microns below the Brooks membrane. So what did we get? Here, the black bars are spectral domain and the gray bars are swept source. And we can see pretty much uniformly that the swept source SNRs were significantly higher than those of the spectral domain. So we looked into the signal profiles a little more deeply, and we picked one patient here, one subject, one single 12 millimeter wide scan, and we picked a location 2 millimeters temporal to the fovea. And we looked at the signal reflectivity profile, and we could see that they're roughly similar. We decided to look at this in 8 of the subjects total, and then average the results. And from this, we can see that the background noise is roughly equivalent between the two systems, but in the swept source system, uniformly, we see a higher signal strength as we go through the retina and the choroid. And this is obviously associated with the various other SNR and the SNR measurements. So we looked at one other measurement that we are calling signal fall-offs, and these are the trend of the results relative to the RNFL signal strengths. And so we see that there are all the retinal layers other than the RNFL. And again, we see that the swept source is performs uniformly stronger or has better signal strength throughout all the measurements, with only one exception, and that's for the RPE for the macular and wide scans. And this presumably is associated or may be associated with the increased absorption from melanin for 800 nanometer light and as opposed to 1 micron light. I want to conclude the talk to you. From this analysis, we've quantified the overall superior image quality with swept source OCT, and the swept source is capable of producing more consistent image quality over a larger scanning area, as we saw from the wide scan results. We showed intensity profiles that show higher foreground reflectivity profiles with the same background noise between systems. And the retinal layer SNRs and signal fall-offs suggest that SSOCT provides more detailed structural information than spectral domain. Thank you very much.